Good afternoon, everybody. This is week 3, lecture 5, homogeneity of production functions and returns to scale. If you go to Landsberg chapter 6 and Ben Sarko chapter 6, you'll be able to get all what I'm talking about here. Today we are going to look at the different types of production functions, and we're going to see what will happen when the farm decides to increase its output in the long run. Is it going to increase or expand the plant size, or is it going to reduce the plant size? Is it efficient for the farm to increase its plants given its available resources, or is it efficient for the farm to reduce its plant size? So we're going to take a look at those ones when we look at constant returns to scale and increasing returns to scale, increasing returns to scale, decreasing returns to scale, and constant returns to scale. And before we move on to that, let us try to find out or determine the degree of homogeneity of various production functions. Are production functions homogeneous? Because most of the production functions that we are going to deal with are homogeneous. So we don't know which type of degree, but we're going to determine that one during the course of this lecture. So let's go ahead and get started. Homogeneity of production functions simply means that if we multiply all inputs of production by a certain factor, let's say we multiply each input. Remember, you have a production function given as Q equals to, let's say, LK, where L is the labor input used, K is the capital input used. So if the farm decides to increase all inputs, let's say by a common factor, let's say T, and if output increases as a result of the increase in input, if output increases by T raised to the power N, then the value of N there is the degree of homogeneity. So homogeneous functions here, simply if we multiply or if we try to increase all inputs by a particular factor, the output is going to increase by that factor raised to the power, raised to an exponent. And that exponent is what they refer to as the degree of homogeneity. So let's take a look at one particular production function here. Let's say Q equals to F of LK, and K is the capital, and L is labor inputs. Then Q is the level of outputs. So if we multiply the entire production function by T raised to the power 0, and then we're going to have T raised to the power 0 there. Now 0 is the degree of homogeneity. So it means that this production function is homogeneous of degree 0. And we said the degree of homogeneity is 0 here. So if a production function is homogeneous of degree 0 is 0, it means that if we increase inputs by a certain amount, output will remain will remain unchanged. So output will not change even if we increase inputs by a certain amount. There will be no change in output. So in that particular case, the production function is homogeneous of degree 0. Now, what can we say about the production function if n is equals to 0.4? Really, if n is equals to 0.4, then the degree of homogeneity there is 0.4. So that means that if the farm increases inputs by a certain amount, the output is going to increase, but by less than the increase in output. It's going to increase by less than the increase in the inputs. If, let's say, the farm decides to double all inputs, then output is not going to double. Output is going to increase by less than the amount that we try to increase the inputs. So if, let's say, we try to increase the inputs like 3-folds, if the production function is homogeneous of degree 0.4, then the output is going to increase by, let's say, it's going to increase 2-fold. Instead of 3-folds, it's going to increase 2-folds. So in that case, we say the degree of homogeneity there is 0.4 and it is less than 1. So it means that if we increase all input by a certain amount, output will increase, but by less than the increase in output inputs. So is this efficient? So this is one typical example of constant returns to scale. This is an example of a constant returns to scale, excuse me. It's an example of a constant returns to scale. So that is to say, if we want to expand the plant size, is it worthwhile for us to increase? Is it worthwhile for us to make the factory bigger or smaller? If there are constant returns to scale, then it is not efficient for us to make the plant size bigger, because that is going to increase cost. It's going to increase total cost as well as average cost. So when when returns to scale is decreasing, the total cost function, the total cost is increasing. Likewise, the average cost of production is also increasing. It is increasing due to the fact that when you try to increase the plant size when there is decreasing returns to scale, there may be some coordination problems. And there may also be some other problems associated with abilities, entrepreneurial abilities. Now, some of the workers may not have the skills, the necessary skills, in order to meet the expansion. They don't have the necessary skills, maybe to operate some of the machines, and so output will actually increase, but it will increase by less than the amount, by less than the increase in inputs. So that is not cost effective. So for decreasing returns to scale, it is not cost effective for the farm to expand the plant size because of this condition, because of coordination problems, or because of managerial skills. People don't have the necessary skills, the entrepreneurial skills, maybe to run, to operate the business. So now let's look at the homogeneous production functions that have a degree equals to 1. So in this case, if we multiply all input by maybe t, then t is going to raise to the power 1. In that case, the production function is homogeneous of degree 1. The production function here is homogeneous of degree 1. In other words, it is linearly homogeneous, and it exhibits constant returns to scale. So in this particular case, when a production function exhibits constant returns to scale, it does not matter. It does not matter whether we increase the plant size or decrease the plant size. Because if we increase inputs by a certain amount, then output is going to increase by that same amount. So in this particular case, a total cost of production is a straight line. It is linear. And the average cost of production is horizontal. So for all constant cost industries or constant returns to scale industries, the average cost of production is horizontal. It is parallel to the x-axis. So let's look at one simple exercise here, and I expect you guys to be able to study this one. Make sure you know how to do it, because the nature of the second midterm exams and the final exams is gonna just look like this. So I want you guys to maybe study this one very well, and I'm taking my time to walk you through this problem so that you'll be able to understand them. They are very simple, straightforward, and I believe everybody will be able to solve them. It does not involve any calculus here, so all we need to do is a little bit of basic algebra. So let's look at the first exercise here. It says identify the degree of homogeneity of the following production functions and determine whether they exhibit constant decreasing or increasing returns to scale. Now, let's look at the first question here, which says the production function is given as 20 k to the 1.5 L to the 0.5. So how do we determine the degree of homogeneity here? Now, I'm trying to move slowly with this one, because I know some of you guys have some problems with math, basic math, but I'm going to make sure that everybody's able to understand. Now, let's look at what happens to that particular production function. Now we are trying to increase the input by a certain amount or a certain factor. We want to increase the input, labor, as well as capital by a factor lambda. Now, look at what I did here. So I took this lambda value, and then I multiply that by k. So that's all you have to do. So remember, we have 20 here, and then I multiply this our input by that. So that's how I increase the input, right? And then raised to the power 1.5. Now remember, we have to put this same exponent up there, and then we do the same thing for labor. You want to increase labor by the same amount, which is lambda, right? And then you can even use any other variable. You can use A, you can use B or C. So whatever you want to use there, you can do that. So it does not matter, you don't need to use lambda there. So, and then this is 0.5, right? That's all you have to do. So you try to take all those terms inside the bracket out, take the lambda out, factor it out. So what do you have? You're gonna have lambda raised to the 1.5, right? Because you know, whenever you have a, b all raised to the power c, is a to the c, then b to the c, right? That is simple. So you are going to raise each of these terms inside the bracket by this exponent, right? So and then you have k to the 1.5, and then lambda to the 0.5, and then L to the 0.5. So remember, you don't have to forget that's 20. You have to include 20. Okay. Now what we do next is to just take these lambdas out. Now factor these lambdas. Just take them out. Lambda 1.5, lambda. So we say lambda raised to the 1.5, and then lambda to the 0.5, and then we have our 20k to the 1.5, and then our L to the 0.5, right? So once we have that, we know in indices, you did indices in high school, or maybe second grade or third grade, I don't know. But I think I did that in second grade, right? So you did indices in maybe second or third grade, and you have lambda raised to the 1.5 and lambda raised to the 0.5. So this is lambda raised to the 1.5 plus 0.5. So you have lambda to the 1.5 multiplied by lambda to the 0.5 is just lambda to the 1.5 plus 0.5. All you need to do is to add the exponent. Just add the exponent, since all these indices are the same, right? So you have these values are the same, lambda, lambda. So just add the exponent, okay? Then we have our 20 here, and k to the 1.5, and then L to the 0.5. There we go. Right? So what do we have here? We have lambda to the 1.5, and then plus 0.5, which is just 1.5 plus 0.5 is just 2, right? So that's how we got this lambda square. That's how we got this lambda square. Now what do you notice? You observe that this same term, 20k to the 1.5, L to the 0.5, is the same as the production function, which is Q, right? Is the same as that one. and then multiply by lambda square. Now, this is how we try to increase the inputs, all inputs. And then what happens to the outputs? Output is going to increase by this factor raised to the power. So this power here is the degree of homogeneity. And since it is equals to 2, then the degree of homogeneity is 2. In other words, we say this production function is homogeneous of degree 2. And so, because it is homogeneous of degree 2, if we increase all the inputs by a certain amount, the output is gonna increase by more than the increase in outputs, the increase in inputs. So returns to scale are increasing here. So this production function exhibits increasing returns to scale. It exhibits increasing returns to scale because if we increase labor and capital by a factor of lambda, it will produce an output level that is more than the proportionate increase in the inputs. That is to say, lambda square is bigger than lambda. Now, you see we have lambda square here, right? But how did we increase the inputs here? By just lambda. And then we ended up getting an output that increased by lambda square, right? It increases by lambda square. So that means the returns to scale here is increasing, okay? So the production function exhibits increasing returns to scale. Now let us look at B here. We do the same thing, right? We just multiply the input by lambda. Then we do the same thing for this other one, lambda k, and then lambda l, and then lambda l here. So, but we have a production function which was given as k plus k to the 0.3, l to the 0.3 plus 5l, right? So, if we try to increase the input by a certain amount, all the input by a certain amount, which is just lambda, we increase capital by lambda, so we have to multiply by lambda. We increase labor by lambda, we have to multiply by lambda, right? So, that means if we open this bracket, we're going to have lambda k plus lambda to the 0.3 times lambda to the 0.7 plus k to the 0.3, k to the l to the 0.7 plus lambda multiplied by 5l. Now, what we do here is we try to we try to factor the common term here, which is just lambda. Remember, lambda to the 0.3 plus 0.7, just lambda to the 1, right? When you multiply lambda to the 0.3 by lambda to the 0.7, you just add the exponents. Exponent, add those two values, 0.3 and 0.7, right? And so when you add those ones, you're going to have lambda k plus lambda raised to the power 1, k to the 0.3, l to the 0.7 plus lambda multiplied by 5l. Now, if you factor this one out, you're going to have lambda into what? K plus k to the 0.3, l to the 0.7 plus 5l. Now, remember, this term in brackets is the same as the production function, which is equals to q, right? And so we just multiply by lambda by q. So what is the result here? We increase the labor as well as the capital input by lambda, then our output increases by lambda. So in this case, because it's increased by lambda, and then lambda is the same as lambda to the 1, the degree of homogeneity here is 1. This production function is homogeneous of degree 1. In other words, it exhibits constant returns to scale. That is to say, if we increase all input by a particular amount, the output is going to increase by that same amount. If we decide to double all inputs, if let's say the farm decides to double all inputs, then output is going to double. So, what is the intuition here? If we have a situation like this, constant returns to scale, right? So it does not actually matter whether the farm wants to increase the plant size or decrease the plant size. It does not matter. It will not add anything. You understand? So it does not matter if there is constant returns to scale, whether the farm should increase the plant size or maybe decrease the plant size. So the issue of constant returns to scale here is just trying to tell or actually help the farm to know whether it is supposed to increase the plant size or decrease the plant size. Whether it's going to do that to increase output or decrease output. Because if the farm is experiencing decreasing returns to scale, then it is not efficient for the farm to increase the plant size. Because if it tries to increase the plant size by increasing the inputs, the output, if it doubles output, output is now, if it doubles the input, the output is not going to double. It's going to increase by less than the increase. So it is not efficient when the farm is experiencing decreasing returns to scale. So it is more expensive for the farm to expand outputs. It is cheaper for the farm to be smaller if returns to scale is decreasing, or if the farm is experiencing decreasing returns to scale. So it is cheaper for them to reorganize, for the farm to reorganize and get a very small plant size, and that will help to increase output. So you all get the point I'm making. So does that make sense? So it is cheaper if the farm experiences decreasing returns to scale. It is cheaper to make the plant size smaller than make it bigger. Because if it decides to make it bigger, then it's going to increase its cost. Rather than reducing its cost, it's going to increase its cost. But if the farm is experiencing increasing returns to scale, it is cheaper for the farm to expand output. It's more efficient to do that, because that will help to reduce its cost. So cost will not be increasing, average cost will fall. So when the farm experiences increasing returns to scale. So that is why, in fact, if you look at this you look at this most of these express package delivery companies, you know, we only have FedEx and UPS, right? You know, because of the process of increasing returns to scale, you know, in the market for mail delivery, that's why you don't see new express packages, you know, entering the market to compete away the profit. So because of that, that is why you don't see new express package delivery companies entering the market. That's why we only have FedEx Plus, right? So um, let's continue here. Um, Now our Q lambda is equal to lambda Q. So this implies that the production function is homogeneous of degree 1. Because by multiplying the production function by lambda, each of the input by lambda, the output is going to increase by the same lambda. So lambda is equal to lambda, right? So there is constant returns to scale here. The production function exhibits constant returns to scale. Now let's look at C here. Now let's since okay, this is okay, B. So just remove this B, this E, it is B, right? So yeah, it is just B. Since B is common, right? So B here is common. We factorize by taking B out, and so we have a QB equals what? B into 3K plus 6L, which is equals to what? BQ. Now again, we want to increase the inputs. We're going to increase by a particular value, which is B, right? And then we do the same thing for the labor by B, right? Then we have 6BL and then 3BK. We take B out. We have B into 3K plus 6L. Now, 3K plus 6L is the same as the output for the production function. That is equals to Q here. So QB equals to BQ. So in this case, the degree of homogeneity here is 1 because B is raised to the power 1. And so the returns to scale is constant here. So this production function also exhibits constant returns to scale. So if the firm increases labor and capital by a factor of B, and output will increase by that same amount by B. So, therefore, the production function here exhibits constant returns to scale. Now let's move on to returns to scale here. What is returns to scale? Now we have just covered the degree of homogeneity or homogeneous production functions. Now let's look at returns to scale here. As I said earlier, sometimes firms may want to decide whether to increase output in the long run or maybe reduce output, whether they should increase their plant size or maybe reduce their plant size. So they can only do that, they can only make that particular decision if they know what their returns to scale is. So the concept of returns to scale help us to know this one, whether the farm is supposed to increase plant size or decrease the plant size. Or we say, is it more cost effective or less cost effective to increase output in the long run? Now, if there is constant returns to scale, it doesn't matter, right? It doesn't matter whether the farm increases output, increases the plant size or decreases the plant size in terms of the cost effectiveness. But if the production function of the farm exhibits increasing returns to scale, then it is cost effective for the farm to increase output. It's cost effective for the farm to increase the plant size. Because by increasing the plant size, the output is going to increase by more than the increase in our inputs. So if we try to let's say we try to increase the input in the production process, then how much output are we going to get? Are we going to get more than more than the increase in inputs. If we don't get more than the increase in input, if our outputs is not more than the increase in our inputs, then that particular venture is not economical or is not cost effective. And it is not cost effective if the production function exhibits decreasing returns to scale. Because if the production function exhibits decreasing returns to scale, then if the farm decides to expand the plant size by increasing more inputs, then the output is going to increase, but by less than the increase in inputs. So does that make sense? So the farm, if the farm decides to increase or expand the plant size by increasing the inputs, then the output is going to increase by less than the increase in inputs. So it means the farm is putting more stuff into the production process, but it is getting less in return when the production function exhibits decreasing returns to scale. So it is not economical for the farm to expand the plant size. It is not economical for the farm to become bigger. It is better to operate a very small factory than operate a very big factory when returns to scale is decreasing. But if the returns to scale is increasing, then it is more efficient, it is cost effective to increase the plant size. Because average cost will be falling, and then even though total cost will be increasing, but it is going to increase at a decreasing rate. It is going to increase at a decreasing rate. And the average cost of production is declining if the farm exhibits the farm's production function exhibits increasing returns to scale. Now, the other word for increasing returns to scale is what? Economies of scale. The farm is enjoying economies of scale. So it is worthwhile for the farm to even expand, maybe bring in more machinery, and hire more workers, employ more capital, and then expand the business. So because returns to scale here is increasing. Okay? So returns to scale here refers to the rate at which output changes as factor inputs change proportionally. Now, we've discussed that one. There are three distinct possibilities here. Either the farm experiences increasing returns to scale, or constant returns to scale, or decreasing returns to scale. So there are only three possibilities there. We don't have any other possibility but these three. Either the farm experiences increasing returns to scale, decreasing returns to scale, or constant returns to scale. So if the farm experiences constant returns to scale, it doesn't matter whether he expand his business or maybe shrink his business. It doesn't matter. It doesn't matter whether he operates a small plant or maybe he operates a very big plant. But it does matter if the farm's production function exhibits decreasing returns to scale. Because if it exhibits decreasing returns to scale, if the farm decides to expand the business, its average cost will be increasing, and its total cost will be increasing at an increasing rate. Instead of increasing at a decreasing rate, it will be increasing at an increasing rate. And so it is not cost effective for the farm to expand its business when the cost, when returns to scale is decreasing. Because here he's going to be putting more stuff in and then getting less in return. So it doesn't make sense for the farm to expand the business. So it does make sense for the farm to operate a very small business instead of expanding its business. Instead of operating maybe a larger plant. Maybe some of the plants will be shut down, in order to minimize cost. But if the farm is experiencing increasing returns to scale, then it is worthwhile, it is cost effective for the farm to increase its plant size. Because by increasing its plant size, it's going to get more because um, um, if it decides to increase the inputs, the output is going to increase more than the increase in inputs. So it's going to gain a lot, and then its cost will also reduce. The average cost of production will fall, even though the total cost is increasing at a decreasing rate, but the average cost of production is declining when the farm's production function exhibits increasing returns to scale. So do you get the point I'm making? So I hope you get this point. Now, we look at, is it cost effective for the farm to increase output in the long run? Well, it is cost effective if the farm's production function exhibits what? Increasing returns to scale. But it is not cost effective if the farm's production function exhibits decreasing returns to scale. Okay? Let's move on. So increasing returns to scale here refers to a situation where the farm's total cost increases, but at a decreasing rate relative to the expansion in output. In other words, the production function exhibits increasing returns to scale if output increases more than the proportionate increase in all inputs. For instance, if all inputs are treble, output will increase more than threefolds. So increasing returns to scale is also known as what? Economies of scale. Now, if you look at the graphs here, this is one example of a farm experiencing increasing returns to scale. You see its cost, its total cost is increasing, even though it is increasing, but it is doing so at a decreasing rate, right? And then its average cost of production is falling, is declining. So that is why it is cost effective to expand the business or maybe operate a very large company or large organization, because there will be proper coordination here. This one, and because of the proper coordination, and again, because everybody knows what is supposed to do, and we have greater entrepreneurial ability here. So because of that, it is worthwhile for the farm to expand the business to operate a very large farm, a very large company. So when we have increasing returns to scale, what we observe here is you have a situation where the isoquants are becoming very close to each other. Now you see the first isoquant is far apart from this one, but production increases, you observe that all the isoquants are very close to each other, right? So the isoquant gets closer when returns to scale are increasing. Take for example, you have a big car manufacturer, a big car manufacturer that maybe experiences increasing returns to scale will be producing lower cost cars. And so it is efficient for that farm to operate that particular business. So overhead costs are very low, they're not very high. And then you have greater entrepreneurial ability in this particular regard. Now let's take one example here. Let's try to do this one. We have a production function. The production function of a particular farm producing pens of the form Q equals to f of Lk equals to 50L to the 0.6 and then K to the 0.8. Yeah. Now, does this production function exhibit increasing returns to scale? Well, we are going to find out. So, what we do here, let us try to increase all the inputs by a certain amount. We are going to increase the input by a certain amount. In this case, we are increasing the input by B. So labor is going to be increased by B, capital will be increased by B. So if we plug in that value B into that production function, we're going to have what? 50. QB equals to our 50 into BL, 0.6. Remember, we have 0.6 there, right? And then BK to the 0.8. Now we are going to expand this bracket. So we have B to the 0.6 multiplied by B to the 0.8. 50 BL to the 0.6 K to the 0.8. And then we have B to the 0.6 plus 0.8. 50 L to the 0.6 K to the 0.8. If we add those two, 0.6 plus 0.8, we're going to have 1.4. And then we have B to the 1.4, 50 L to the 0.6, K to the 0.8. Got it? And so, if you look at this term here, 50L to the 0.6 and K to the 0.2 is the same as the production function Q, right? It is just the same as that. So that means B to the 1.4 is multiplied by just Q, right? And so QB equals to B to the B to the 1.4 multiplied by Q. So when we increase all the inputs by B, what happens to the output? Output increases by what? A factor of what? B raised to the 1.4, right? So that means here, the degree of homogeneity here is 1.4, and returns to scale are increasing. So this particular farm production function exhibits increasing returns to scale. That is, if we decide to increase inputs by a certain amount, output is going to increase by more than the increase in inputs. Returns to scale increasing here. Now let's look at the other case of decreasing returns to scale, where when we increase the input by a certain amount, what happens to the output? When we put in more stuff, we get less in return. So that is a decrease in returns to scale. So in this particular case, the average cost will be increasing here, right? The average cost will be increasing. So also is the total cost. Total cost will be increasing at an increasing rate. It is not going to increase at a decreasing. It is going to increase at an increasing rate, as you see here. Total cost will be increasing at an increasing rate. And also, we have the long run average cost curve here that is also increasing. Now, this is because we have a lot of coordination problems here. You know, if the farm is experiencing a decrease in returns to scale, it wants to expand, maybe the plant size, there will be a lot of problems. The problems will arise because of what? People don't have the requisite skills, you know, to actually operate the machines. You know, if the plant decides to increase, you don't have the skills, necessary skills. And so that is going to affect, that's going to increase the cost. So that is why it is not efficient to expand the business when the farm is experiencing decreasing returns to scale here, because cost will be increasing. See, the average cost is increasing. Likewise, total cost of production is increasing at an increasing rate. So The decrease in returns to scale here occurs because of what? Decrease in efficiency. It also occurs because what? Declining entrepreneurial abilities. People don't have the abilities to actually perform certain tasks. And so costs will be increasing. Productivity is going to be very low. The productivity of the workers is also very low because they don't have the entrepreneurial abilities to perform most of the tasks. So it is not like increasing returns to scale where you will have workers that are highly productive, that have the entrepreneurial abilities, and maybe to operate on to perform different tasks. So you may have certain maybe one person maybe doing some bookkeeping, you know, and then or maybe doing two types of performing two types of tasks, or maybe you have two maybe specialized machines. The farm will try to get like specialized machines. That is by um, increasing capital, and that will also help to increase the outputs. Okay, and then the isoquant here, the isoquant are far apart. They are distinctly far apart. They are not very close, like case of increasing returns to scale. Again, there will be tremendous difficulties in getting the right employees for the job. So you have a lot of coordination problem when the farm exhibits, when the farm's production function exhibits decreasing returns to scale. So these are some of the problems when the farm's production function exhibits decreasing returns to scale. Now, if we look at the isoquant here, they are all far apart. Isoquants are all far apart. They are not very close as in the case of increasing returns to scale that we did earlier. Now, let's look at one typical example, basic math here. We try to see whether this production function exhibits increasing, decreasing, or constant returns to scale. We just try to increase the input by a certain amount. Let's see what happens to the output. If we do that, we have what? C to the 1/3, L to the 1/4, right? Because CL to the 1/3, you have to raise both of these two terms to the 1/3, right? And then CK to the 1/4 is just C to the 1/4 and then K to the 1/4. So if we factor this C out, the maybe the term that we used to multiply out, we're going to have C to the 1/3 times C to the 1/4. Now remember, in indices, A to the X times A to the Y is A to the X plus Y, right? So we'll do the same thing here. So this is just C to the 1/3 plus 1/4, then 30 L to the 1/3, K to the 1/4. So what happens here? If we add these two, we're going to have C to the 7/12, which is the same as C to the 0.58. Now remember, this 30 L to the 1/3, K to the 1/4 is the same as the production function, which is Q. So we have C to the 0.5 Q. And so what happens here? Production output is going to increase, but by less than the increase in input, because the degree of homogeneity here is 0.5. Because this exponent is less than 1. Okay? So returns to scale here are decreasing. So the farm here exhibits decreasing returns to scale. Okay? So constant returns to scale. If by increasing all inputs by a factor, let's say C output increased by the same amount, then the farm exhibits production function exhibits constant returns to scale. So here it does not matter whether the farm is bigger or smaller. It doesn't matter. In terms of cost effective, it doesn't matter whether it's bigger or smaller, as long as it exhibits constant returns to scale. Because if he puts in maybe $100 worth of inputs, it's going to get $100 worth of outputs. So it doesn't matter whether the farm is bigger or smaller here. Okay, if the farm exhibits constant returns to scale. So when the farm exhibits constant returns to scale, the isoquants are all what? The isoquants are all equally spaced. They are all equally spaced, as you can see the diagram here. This is an example of constant returns to scale. So when the farm exhibits constant returns to scale, all the isoquants are equally spaced. Okay. Now, I've been doing the talking. I've been doing the talking a lot, and then I've been doing the explanation, all the talking and all the computation. Now I want you to go down and sit down quietly. Take these problems. Take a piece of paper. Try to solve these ones. Try to determine the degree of homogeneity of each of these production functions. I know you'll be able to do this one because if you have gone through the video lecture, this one will not be a problem for you. This one would just be like drinking water. It will be so easy for you. You can be sipping your cup of coffee or maybe tea, whilst doing this one. You have your cup of coffee or maybe your tea, whilst solving these problems. So this is just like for you to practice. If only I am doing the problems all the time, I'm working, solving the problems all the time, and then you are not doing anything, so you will not be able to do them. You will not be able to do them. So just try to sit down quietly and then see if you can come up with something here, and then if possible, you can even represent the isoquants, for each particular scenario or each particular case. Try to represent this. Try to see if the isoquants are equally spaced, or they are very close to each other, or they are far apart. If there is decreasing returns to scale. So try to do those things, and hopefully, I am going to post some lectures on costs, theory of cost, and perfect competition and monopoly. So I intend to post all those lecture notes this week, and then we wrap up with general equilibrium. Then next week we're going to move on to game theory and oligopoly and oligopolistic markets. So I don't know, game theory will be fun because it will not be so hard. And then hopefully the 7th week, we're going to move on to externalities and public goods. I believe that topic is so interesting, and that's what I love. I love to teach that one, externalities and public goods, and the issue of moral hazard, asymmetric information, and the issue of the concept, the issue of insurance. So why do people insure? Why do they ask for insurance? Why? And then why do we normally put more premium when a person got involved in an accident? Is it because of the moral hazard issue or what? So these are some of the things that we're going to discuss under asymmetric information and moral hazard, as well as the issue of risk under uncertainty. So we're going to do that one in the final week before the finals. So I believe some of those PowerPoint slides have already been posted. So if you want to read ahead, maybe you can go and do that. If you want to read ahead, those notes, those lectures have been posted for week 7 and then week 8. So if you are that type that want to go move ahead, so you can do that. And, hopefully, I'll try to um, put in all those exercises. I want you guys to have a lot of practice before the second midterm, because I need you guys to do extremely well in the second midterm. And, I know some of you guys have some difficulties with these multiple choice questions. You seem to be doing well when it comes to essay questions, you know, but when it comes to true or false questions and explain and multiple choice, some people don't do well, you know, with multiple choice. I'm not good in that. So, but you don't have to worry about that. So, but let's just try. I just want you to do this one, go home and then practice this one. And if you have any problem, any difficulties, please feel free to call me. Please feel free to send me an email. I will respond to your email promptly. Okay? I wish you all the best. Bye.